Good morning, mathematicians. I'm going to probably just struggle through this thing I'm trying to struggle through in front of all of you. Just do some very boring reading.
Good morning, mathematicians.
I don't know, unless you guys ask me some questions. That's probably what I'll do. Try and solve the mystery I'm stuck on. Well, let's pop over to Reddit real quick. Just see what's happening there. Good morning, Quality. Good morning. Yeah, okay. So what's this thing I'm reading? I'm trying to understand, there's some paper. Gosh. Should I be doing this on stream? Should I just be trying to read this paper I'm trying to read on stream? I feel like I've got to stop and explain too much of the notation. Surely it's not entertaining for all of you. Well, let me tell you at least, this is the statement I'm trying to understand. There's some surjection of modules. Well, actually, according to some people, it should be an isomorphism. I believe if we have a surjection of modules here, then this will in fact be an isomorphism. But yeah. But I feel like this isn't right. Yeah, so I'm going to scroll back, all the way back. Let's start at the beginning of this paper. Let's understand it. Okay. We have our induced representation. We have the affine Hecke algebra. Lustig mentioned, oh yeah. Yeah, speaking of yesterday's Lustig beef, where did he say Lustig? I can't read, I can't see. Yeah, there we go. Kasdan Lustig basis. Yeah. But also yeah, also here. And here. No Kashiwara mentioned. That's on the other side of my research, though, where he most definitely is. Yeah. Okay. HW is a Hecke algebra of the Weil group. What else notation do I need here in order to try and hash out these computations? The extended Hecke algebra. CT? What is CT supposed to be in this case? The function field CT. Okay. So that's being interpreted as the rational functions on the torus. Wait, a rational function of the characters, though? Ay. Oop. See, this whole thing is very confusing to me. Tau may be viewed as an element of the torus. Tau is a character. Tau is a character. So that's weird to me. I guess it has a co-character partner. There's the co-character that's dual to it, and then you can evaluate that co-character. So we have Chi, what he calls Tau, but I'm calling it Chi, is a character of the torus. No, but this is a complex character, so yeah, I don't know how he's saying that this can be viewed as a element of the torus. This is my life every morning. Trying to understand what the hell people are talking about. And hopefully getting somewhere. Now, tau may be viewed as an element of T. Well, I mean, the other thing is we could think about it, I guess. Tau is, or Chi in this case, is what? It's some external tensor product of characters. And so I could say evaluate this. Well, have I ever had to read proofs of the Weil conjectures for my research or a class? No, never. Never. I've definitely looked it up a bit. You're right. This is exactly what math is all about. Although actually there is a book related to my research called The Fourier Transform, and then it's the greatest misspelling in all of mathematics. Fourier Transform, or what is it called? No, perverse sheaves. And the laddic instead of L dash addic, L apostrophe addic Fourier transform. And this is part 2. I think it's part 2 of a 2-part series where basically one talks about the proof of the Weil conjectures via this machinery. And one of the steps there, I think, is the decomposition theorem, which is actually essential to my work. I wonder, laddic. I'm sure I have it on my laptop. I know I have it already, but oh yeah, here we go. Freytag-Kiel, cohomology, and the Weil conjectures. Yeah, this is part one. This is part one of the book. I think so. I could have the order mixed up, but I think this is part one. If you ignore the Riemann hypothesis, the proofs are quite elegant and formal. Really? Oh. You're reading Milne's L-adic cohomology and wonder if it's worth trying to get ahead to the section on the Weil conjectures. To go ahead to the section. Yeah, I mean, there's only one way to find out. You go ahead and jump ahead and see if it makes sense. Yeah, let's see what do we have here. A whole bunch of basic stuff on Weil cohomology, rational Weil zeta functions. Oh, and then Deligne's proof of the Weil conjecture. Why don't we jump ahead right now? So what the hell is going on in part two? That's my question. They already give Deligne's proof. 249. Actually, let me pull up the. This is Deligne's first proof, though with left chest pencils. I see. Which is not as elegant, presumably. Let's see. What's the other? His Weil2 paper is more refined, which then proved using the Fourier transform. I see. So that's probably the part two. I know I have this book. Maybe I'm looking up the wrong title. Weil conjectures. Perverse sheaves and L-adic Fourier transform. The general Weil conjectures, part one. Formalism of derived categories, perverse sheaves. And Springer representations. I forgot that was in this book. Wait, is that where it ends? What else is supposed to be in here? Where's the big punchline of this book? I should know. Okay, well, let's go have a look at book one. In this section, we formulate the Weil conjecture about the zeta function of a smooth projective variety. Use a corresponding notation for mappings and sheaves. Let this be a constructible L-adic sheaf on the variety. This is its inverse image. We recall the vague growth and decay series for the sheaf. Yeah, I guess they're just writing down all the setup for everything. And then maybe they go through the inelegant proof. Hello, Matthias. Hello. The eigenvalues. Right, so this is just the statement. And then the proof. No. I wonder if anyone's ever proved a number is algebraic using this in a non-trivial way. Yeah. Office hours is back, indeed. Office hours have been back for a little while now, actually. Believe it or not. Word hasn't gotten out, I suppose. But we've been back for a little while now. Okay, I guess I should yap about something. Instead of just staring at documents the entire live stream. Presumably. Although I do want to stare at one particular document. I want to stare at this document until it makes sense to me. Yeah, how do we view Actually, this doesn't make sense to me at all. How do we view a character as an element of the torus? It would be different if this was a character going into the p-adic field. Because I could take these things to be integers, and I could take this to just be q to the power of these integers. That would definitely lie within my torus. But I don't know what the hell is going on here. Because in general, these A's should be complex numbers. How do I define subsequences? The definition in the book confuses me. Given a sequence, A sub n, right? Well, let's think about what should a subsequence be, right? So let's write out a stupid number of terms. A subsequence should be a sequence, right, made out of the elements of the original sequence, but should appear in increasing order, right? So maybe for our subsequence, this would be the first, this would be the second, this would be the third, and this would be the fourth, and so on and so forth, right? Okay, so we need to create a new sequence, right? So if this was our new sequence, then say B1 would be, in this case, A2. B2 in this case would be A4. B3 would be A5. B4 would be A7, and so on and so forth, right? So in other words, a different way to write this is to notice that each element of the sequence, B sub j, right, is really, well, we know it's some element of the sequence A, and so we could imagine writing the index that appears here as a function of that j, right? So we might call it n sub j, right? So for our particular case, n sub 1, so of course I'm thinking of this n of this index as a function of j, so you might even be tempted to write, n of j or something, which is fine, but n sub j is, I don't know, we could take that as like a definition, right? So we're looking at different indices that depend on j, right? So again, just repeating the same idea, n sub 1 in this case would be 2, right? Because B1 is A2. And then n sub 2 would be 4, since B2 is A4. And n sub 3 would be 5, and n sub 4 would be 7, and so on and so forth, right? So finally, what we need to make this so I guess the idea is we want to come up with a definition of a subsequence a n sub j, right? So, and we want it, just like an ordinary sequence, it should depend on numbers that go linearly from 1 to infinity, right? So that's like the sequence here. But instead of having to write these b's, right, by using this notation, we're able to just write it with reference to the original sequence. And then the final thing to take care of is this fact that, again, I don't want to just grab an arbitrary assortment of numbers from the sequence and rearrange them into any order. Rather, I want those numbers, I want to take those, I want to make sure they're increasing, like as 1 goes to 2, I want to make sure, so the index of b's are increasing, I want to make sure the corresponding indices of a are increasing, right? 2 goes to 3, 4 goes to 5, 3 goes to 4, 5 to 7. And so that's the final part, which you commented there. We just want to make sure that if j, if k is bigger than j, then we want to make sure that nj is bigger than nk, right? And so, in fact, it suffices to just prove that. Sorry, I'm using k a little bit different than you did in your comment, but it suffices actually to just demand that n sub j plus 1 is bigger than n sub j. And from this, it would follow for all indices. Yeah. So that's that. Yeah. No, someone help me with my confusion. Reverse office hours. You guys explain this to me. How do I view this character as an element of the torus? I can't, right? Am I losing my mind? I must be losing my mind. I must be losing my mind. Yeah, I don't think there's any other assumptions on tau here. It's an unramified character. Yeah, so it's determined by some tuple of complex numbers. If I'm in a p-adic group, I can't put things to the powers of random complex numbers. I feel like that's kind of a big deal for understanding the formula I wanted to understand later, though, because he interprets other things as functions on the torus. Yeah. So that's confusing. Yeah, wait just a second. Yeah. G is a reductive p-adic group. And theta is isomorphic to the coordinate ring of a maximal torus. Oh, wait a second. Maybe this is true. Because, right. Maybe this is true, actually. So theta should be, capital theta here, should be, actually, theta should be the co-characters, right? We can bring in the complex numbers later by taking some sort of formal span. But this should be the co-characters of the torus. But now, okay, hang on. We're getting somewhere. We're making progress. Where was that here? Where was he talking about the coordinate ring? Coordinate ring of a maximal torus. Wait, in the complex Lie group. No. Okay. Oh, hey Nick, how's it going? I plan to reply to your email at some point today, shortly after this. I'll reply to your last email. Right. But okay. Yeah, typically one takes, I mean theta. No, that's true, right? Because this is the affine Hecke. Right, it should be isomorphic to the coordinate ring. Oh, okay. Yeah, this is oh, Matthias, your comment didn't show up on screen. Sent it minutes ago. Oh, which comment? Maybe if you tried to link something, sometimes it it won't let you send links or something. Or if you said something nasty. Maybe YouTube auto censored it. Okay, now this is confusing though, because here the T torus. Hey, Femnal, it has been a long time. Okay, so he's letting T be the torus in the dual group. Okay, so that actually makes sense. Okay, that actually makes sense. Because, so let me just say this. Have I heard of the book From Calculus to Cohomology? I think so. I'll pull it up in a second. because here's the thing. So like the affine Hecke algebra, let's say I've got so many notations for it, attached to GLNF is basically generated by TW E lambda, subject to some relations that I don't know what, not going to say now, but where W runs over the Weil group, lambda runs over the co-characters of the torus. Yeah, and this is some like, well, it's a complex algebra. So you basically look at like the complex span of these things and their products and subject to some relations, blah, blah, blah. So, lambda, right. So lambda being, but this is isomorphic actually. So there's this is isomorphic to, you can attach a Hecke algebra to GLNC because somehow it really is just defined in terms of the root data, where we have TW going over the Weil group of GLNC, but that's actually isomorphic to the Weil group of the p-adic group you started with just by root system nonsense. And now we'll call this E omega, and here omega will go over the characters of what I'll call T hat, but the root system of GLN C, I mean, the way that we build this group is by taking the dual root system. So we actually do have an isomorphism between these things. Yeah. Okay, so mystery beginning to be resolved. Does my chat not like the mention of ChatGPT? I don't know. I haven't put on any settings that says like don't show me ChatGPT stuff. I don't know. Try using a different acronym for it or something. Yeah, I don't know. From calculus to cohomology. Contents. Why does this page suck so bad? It doesn't even have a cover. The table of contents looks gross. Who made this web page? Not that I have any skills. You just told me that GPT, that you could use GPT when you asked for advice? Sorry, I'm not sure. I'm not sure what the statement is there. Yeah, I guess this is yeah, supposed to be to try and slingshot you from basic calculus to de Rham cohomology. Ooh, wow, there's all sorts of stuff here. Euler class, Thom isomorphism. Oh, that's cool. Legend has it that they tried to make my supervisor teach a calculus course 1 year, and at some point he ended up talking about the you know, he's like, well, if you have to integrate things, you need differential forms. And so legend has it in like a first year calculus course, he was talking about the alternating algebra at some point. The seminar at your university for next semester will be based on this book. You've learned about Durham cohomology last term, but you're thinking about sitting in. Yeah, may as well. Why not? Why not? Especially if it gets to these higher level theorems. That seems pretty cool. Minutes ago, I asked chat for advice. Yeah. It's not actually awesome at math. Actually, I completely disagree. It's good at finding references, but it is not good at doing math. I would not ask it to. It still hallucinates nonsense way too many times. So, oh, you're taking a seminar of K-theory, so it's already covered. Yeah. Well, hey, whatever. If it's a fun topic, I mean, if anything, right? If it's a seminar or course or something, then, for maybe the younger, less experienced people in the audience, it's good to have more experienced people there to chat and answer questions. So, yeah. You could be in the seminar as more in more of a leadership capacity. Do I know about the McKay correspondence? I've heard of it. In fact, this is like the ADE thing. Is that the McKay correspondence? The sort of crazy mythical. Yeah, I have some like near numerological thoughts about some of these crazy things. Yeah, a subtle correspondence between the theory. Oh, okay, this is a more specific thing. Finite subgroups of SU2, the corresponding orbifold singularities, and that of simple Lie groups falling into the ADE classification. Right, so yeah, it does have something to do with ADE. Interesting. What's the... Okay, so here's a list of finite subgroups of SU2. But how are you getting these other simple Lie groups? How do those show up? Hell yeah, we love our E8. McKay quivers. Yeah, there's something about where you take like the quotient of C8 by some group action, and then there's like a singularity at the origin, and somehow there's this post from John Baez, and somehow you take a blow up of the singularity, and then somehow like E8 appears, and somehow you can read this off from the Dinkin quiver somehow. I don't understand it at all. But it sounds so cool, and I want to understand it one day. Oh, equivariant K-theory. Hell yeah. Very interesting. Yeah, unfortunately, I can't say all that much about it because I don't know all that much about it, but let's see. Yeah. I mean, this just has C2 modulo some group action. Yeah, is G, I guess is G's the simple Lie group in question. And you're looking at, oh, maybe these arise somehow as like, oh, G is, right, okay, so G is, you look at finite subgroups of SU2 acting on C2, and you take some quotient, right? More on this on McKay quivers. Okay. So for a finite group, linear representation, finite dimensional complex space. The Mackay quiver is a quiver whose vertices correspond to the irreducible representations of G. Okay. Where the edges are weighted by the coefficients in the expansion into E-reps of the tensor product of representations. You've been reading the Mackay correspondence, the Coxeter element, and representation theory by Costant. Maybe I should... How do I copy, paste? No, just let me copy, paste. Oh. Okay, I'll just have to type it in manually. I have to go soon. I have to go teach. The Mackay correspondence, the Coxeter element, and Costant. I'll just type that. Should be enough. Interesting. Oh, yeah. And that's all of exactly this stuff going on. I see. Well, let's look at this overview here. Right. Okay, so somehow, right. So we're looking at tensor products. We look at the multiplicities that show up when we decompose the tensor product. That tells us how to draw the edges. That is cool. That is super cool. Okay. So then Mackay says that the Mackay quivers are the Dinkin diagrams that show up from the ADE classification as the ADE singularity. So, maybe that somehow has to do with this other thing that I mentioned when you take a blow up of the singularity. This has something to do with the fact that you can read like the manifold that shows up from the diagram. Jesus. This stuff looks crazy. More precisely, if one uses all irreducible representations, then one gets the extended Dinkin diagram, where the extra node corresponds to rho naught. This is the trivial representation. Okay. Fascinating. Some equivalence of K-theories thing. Yeah, see, what I really want to know, there's, let me see, under John Baez, E8 as blow up of singularity. Maybe this will show up. Yeah. Maybe it's in here. Yeah. So this is this is a related thing. This is something I've always wanted to understand. I never quite dove into fully properly. Take a finite subgroup at the has a singularity at the origin. Take a blow up, but we want a minimal resolution, which means a smooth variety, 1-to-1 except at the origin. And the points that map to the origin lie on a bunch of Riemann spheres. There's one of these spheres. Oh, see, this is interesting. I really want to understand this. Like, why is this true? So apparently there's, you write down these diagrams. Which I guess the way you get the diagram is what we saw on the other page through the tensor product thing. We have a Riemann sphere for each dot in the diagram, and two of the spheres intersect if and only if their dots are connected by an edge. Crazy. This is crazy. This is crazy stuff. In particular, if gamma is the double cover of the rotational symmetry group, right? The binary icosahedron group, or dodecahedral group. Then we get the E8 diagram. Oh, in general, whenever you have a triple of numbers obeying this inequality, you get a finite subgroup of SU2 that contains rotations of those orders. But the puzzle is this. Why does resolving the singularity? Yes, indeed, this is the puzzle. Oh, and it turns out there's an explanation here. Okay. I guess gotta go read that paper. In a nutshell, you start by blowing up C2 at the origin and getting a space containing a copy of the sphere on which gamma acts. Then that new space has further singularities coming from rotations of those orders, and when you resolve those, you get more copies which intersect. I would like to understand this better. Wouldn't we all? And more vividly. I want a really clear understanding of the minimal resolution. Yeah. Very interesting stuff. Very interesting stuff. Yeah. But then this makes me wonder, what about other cases? So these are cases where you have finite subgroups of SU2, but if this inequality goes the other way, then you get like hyperbolic tilings, and you get other triangle groups. So what happens there? That's my question. Right, what if we take the 2-3-7 tiling? See, every time it's bad that you mention this, because every time I think about this stuff, I just waste a bunch of time going down a rabbit hole, never really understanding, but maybe getting a little bit more each time, and thinking about the crazy ways that these wild things like the ADE classification intersects with this thing. There's something to do with like Hurwitz groups, right? Yeah, what is it? Hurwitz surfaces. Hurwitz surfaces. Yeah, that's a keyword. So the way ADE is tied to the resolution of singularities, if surfaces, is via this process of resolving the singularities. Yes, exactly. Yeah, so the claim is basically, that this diagram basically tells you that the claim is that basically if you go through this process, depending on the finite group that you took, you'll get some diagram that fits into the ADE classification, and you can read off from that diagram basically what your resolution looks like. Yes, exactly. Yeah. But yeah, see, I want to know, like, what about these other groups? Can you realize them as, what about these other triangle groups? Do they show up as, I guess they're not finite subgroups of SU2, but like, is this a finite subgroup? Does this show up some other way? I know that there's some way to interpret, like, I think, like the Klein Quartic and was it Klein, Bring, and Bolza are supposed to somehow, you like loosely interpret this as being some like ADE type thing as well, but this is now we're getting into mysticism. Are they subgroups of SU2 still though? Maybe they're infinite subgroups now or something. Yeah. Anyways, I gotta go. Time to go teach. So let's go prove stuff about the ADE classification.